it a really good try, but don't be afraid to make a mistake and then ask, because it's only 5% of the mark. And the idea is to prepare you also for answering questions like that on a test. So hopefully they're actually helpful, the homeworks, and maybe interesting too. Okay, so take a look at it, and if you have questions, try to ask me soon, because if you try to do it the night before, you may become overwhelmed. Okay, the other part is when you're doing things like converting Euler poles into plate velocities, this is a bit of a pain to do by hand. You can do it by hand, but you can also write a little program to do it for you, as long as you're careful. Things can go wrong when you code it, but it will be really quick to use in any kind of situation, right? You just have something that calculates cross products to make sure that you convert the plate rotation velocities to linear velocities at a point, and then you can use it for all the questions. So that may save you time. For those of you who have phobias about programming, you don't have to. When I was a student, I remember sitting down and calculating cross products by hand before finally convincing myself it was better to just make a program, but you can do it by hand. Okay. Okay. Any other questions or concerns for now? Okay, so let's get started on the part about plates. I put a little introduction on block known because it's a little bit, one of the things that's difficult is to say, okay, why are we doing things in this order? Why are we doing things in this way? One thing that you did in physics, for example, was start with what are called kinematics, okay? So remember those equations for, if I want to calculate displacement based on a velocity, knowing the velocity is constant, I have a little equation x equals v times t plus v naught, and then there's all the more complicated ones with acceleration. Then you did it in circular motion, right, with angular velocities and angular speeds. When we talk about plate motion, we can pretend plates are little flat things moving around like this, right? The rompecabezas that we saw. And we can get a lot of useful information just by measuring relative plate rates and using them to calculate velocities. There's also a part here that we're going to mention paleomagnetism, because if you guys remember, paleomagnetism was one of the ways we knew that the magnetic pole appears to wander around in different ways for different continents. And that allows us to actually track the path of the continent, okay? So a question for you guys. When you guys did structural geology and tectonics, for example, did you use any of these models for plate reconstruction, like Nouvelle or any of these? Does this sound familiar? How did you find out Euler poles, or does anybody remember? Or do past plate reconstruction? No, never. Okay. Well, if you think about it, one thing is, if I have a spreading ridge, okay, the magnetic reversals and the age of the rocks can tell me how fast that spreading ridge is. That's one thing, right? So I, without any information about current velocities or any knowledge about the past, can just look at, say, the mid-Atlantic ridge and say, this rock at 1 kilometer is X million years old, and I can say the spreading rate is this much based on basically the velocity of the plate times time. Now, that works for a certain amount of time. What happens is, as you know, it's not always linear. We have Wilson cycles which tend to bury information. So what we can get from this are recent past, and I say recent by millions of years, in plate motions. For example, the Atlantic ridge, how old is it? No more than maybe 100 and some million years. So before that, I have nothing, but for those past 100 million years, I have information on how fast Europe and North America were separating. So that's one part of a plate reconstruction. I can also see the transform faults around this ridge and actually draw to get where the pole is. I'll show you a diagram because I know it's not so easy to just think in your head. So the transform faults give us information, but we can also see offsets, right? So if we have a geological map and we make a crack in it and we move it, we can estimate based on how far away the rock has moved, how long that fault has been there, and how long ago we had the rocks aligned, right? So these things have been used to create what are called plate velocity estimates based on only geological information. We now have something that's more applicable for modern times, which is the geodetic information, so GPS and so on, that measures now. The problem is we can know the plate velocity now, but that tells us nothing about what the plate velocity was a million years ago, right? We can assume it was constant for a while, and the geology supports that, but it has its limits. Paleomagnetism gives us more, because we can have continents that have been there for millions of years, millions, hundreds of millions of years, recording magnetic reversals and wandering poles. And we can actually trace the path of the continents without any other geological information or any information about velocities that are measured right now. Okay, so paleomagnetism is really key for understanding, you know, when did Pangea happen and where, right? And possibly before. So this is part of the reason we know that maybe there were several Wilson cycles, right? So we'll talk a little bit about what you can do with the magnetic data, and that's basically just doing geometry on a sphere, okay? So this is all kinematics. We've said nothing about force, right? We're not applying forces. We're not doing dynamic equations. We're just saying stuff moves. Velocities are related to accelerations, and rotations are related to linear velocities, and we can do all that with some simple math. So we're going to start there before we start talking about plates being real objects with properties and masses and things like that. Okay, let me see if I can share this thing. Let's see, that window. Okay, I don't know, I'd always said. Okay, so have you guys talked about representations of plate boundaries in this way? Because I don't know what you've maybe seen before, but like a subduction zone on a map would look like this, right? And this hopefully is familiar to you. Now, what we usually do is those little arrows, the little bumps, appear on the side of the overriding plate when we're talking about a subduction zone. And one thing we do is we say, if I put velocity of A with respect to B, what I really mean is I hold B still and I move A, and that velocity is the one I mean by VAB. Is this something you guys have seen before?
Sí.
Okay, excellent. Where did you see it? Was this structural geology maybe, or geology introduction?
Introduction.
Okay, so it's been a little while since you've done this. Okay, so this saves us time. It's a formalism that makes it easier to do calculations. Remember our problem of point of view and reference frame. If all the continents are moving, which one is holding still? Well, the question really, the answer is probably none of them. If we're looking at a frame of reference that depends maybe on you know, the axis of rotation and some hotspot we may want to choose, which we can get into this later. But all the continents are moving around. So when I say velocity of plate A, it means nothing. But if I say plate A with respect to B, what I mean is if I hold B here and move A, how fast is A moving? Okay, so this is a little bit back to Fisica Uno and relative motion in different frames of reference, but hopefully that's also a more recent review. So we also have ridges, which we sometimes designate with these double lines. So like two lines like this, and then the arrows go like that. When we talk about spreading rates, this can be a little bit confusing because I might, some places quote a half spreading. So let's say we took this example A. I can say plate A moves to the west by 2 centimeters per year, and plate B moves to the east by 2 centimeters a year. That's a half spreading rate, and sometimes you'll see it that way. You'll see 2 arrows, 2 and 2, okay? But really, if I fix plate A, what I'm seeing is plate B is moving with 4 centimeters a year to the east, okay? So be careful when they mention spreading rates, that they don't mean half spreading rates, which is different than velocity of A with respect to B. Okay, so that's the only caution there, which tends to cause a little calculation mistake. And transforms usually have these little arrows, right? So this should be familiar from mapping when you see motion on a fault. So transform boundaries are exactly put like transform fault diagram with the 2 little arrows. Remember, I can have many kinds. Now this is, I don't know if you guys have seen this. This was Tuzo-Wilson's analysis of the types of possible transform faults. Okay, really they're dextral or sinistral, right? And remember, if I stand on one side of the fault and I see the other piece of crust moving to the right, it's a dextral one. If it's moving to the left, it's sinistral. How do you say this in Spanish? I'm not sure if anybody could translate.
Siniestro.
Okay.
Sinestral.
Sinestral. Okay, sinestral and dextral, or no? Am I making that up?
Sí,
Okay.
dextral, sinestral.
Okay, but these can happen because of different environments. So actually, Wilson identified 6 types of places where you'd find this, right? So remember the mid-Atlantic ridge that opens like this. If I have velocity that's faster here than here, I have to crack the crust a little bit in order to have this moving faster, right? It's like saying if I have this book and I want to pull it apart, if I pull it apart faster here, I have to make a lot of little breaks so that this piece can move slower than this piece, and this piece can move slower than this piece. So I have to make these transform faults. So that's one. That's what we see in the first diagram, right? But I also have other combinations of plate boundaries that will cause me to have transform. So I can have a transform fault in between 2 plates that are subducting, right? I can have a ridge near a subduction zone, and I have to crack the plate this way so that this subducts and the neighbor doesn't, right? So these are different ways of creating transform faults, basically. And why do we care? We care because it tells us something about the evolution of the plate. And I wanted to show you this example because this is kind of a famous example, which maybe you've studied. Where did the San Andreas Fault come from? We have quite a complicated thing here. In the Pacific Northwest, we have subduction zone. And then for some weird reason, we get a transform fault all the way down the rest. Okay, and we can see some ridges here which look like they're about to go under. The history of the San Andreas Fault makes sense when you start doing velocity diagrams and see how, for example, a ridge can subduct and change the subduction zone into a fault. Did you guys ever talk about this type of thing? Like how plates boundaries evolve in time? If it's new, that's fine because we'll go into it in some detail, but I wanted to see if it was you already knew and it would be boring. But maybe millions of years ago. Okay, so yeah, if you did it, it might have been in geology or maybe geostructural geology and tectonics, so it might have been a little while ago. Okay, so let's start with a flat Earth assumption, which works when I assume that I'm looking at a small space. Okay, now I'm gonna show you this link because you might find this fun for people who like to sit up and think of strange. Yeah, there can be aborted subduction zones that just die. So sometimes subduction zones die because a slab breaks off. This, I can show you a neat little thing. Let me put this link first. Okay. So I'll get back to your comments, Santiago. This is just, I think it's just a professor who likes to think about weird things with his students. And he came up with this example of, like, let's say I'm on a mountaintop and the highest mountain in the country. Can I see the lowest point in the country from that mountaintop? Assuming I have binoculars and I'm not limited by how good my eyes are. Okay, so we're just going to assume I can put a telescope if I want. Can it actually be seen? This is an interesting question because remember the Earth is curved. Obviously from here I can't see China even with perfect vision. So where is that limit? When does the Earth's curvature matter? If I'm sitting in this room, I can see across the room and it looks flat. Actually, probably the floor is flat. But if I'm standing in, I don't know, Nevado de Tolima, and I want to see Onda, can I? If I just like keep the mountains out of my way and look?
No, eso ya es muy lejos. Es muy lejos.
Es muy lejos. Okay. So if you're looking for fun problems to worry about, this guy has a little discussion about this, but you can actually figure out where the horizon is. Like if I look and I see the Earth seems to be flat and circular all around me, right? But the horizon, as you guys know, if a ship disappears, starts going away from us, it doesn't just get smaller, it also seems to sink. And that's the curvature of the Earth. The question is, where is that point for us? Okay. So this is a fun problem to think about. But if we're going to look at things like triple junctions and boundaries, I care right about here and maybe not far away. So I can do this analysis. I can assume, for example, that if I have a plate boundary here, that this velocity is not so different from this one and this one and this one. If I look 100 kilometers this way or 200 kilometers this way, yes, it will matter. And I'll even get a transform boundary in between. So all that we're going to talk about today is linear velocities, which you've seen in Física 1. Just maybe you didn't think about them this way before. And it can tell you what's happening, where the plates will go and where they've been and so on. Okay, so here's the convention. I can do A, V, B. That the one on the right tells me which plate I care about moving, and the one on the left is the one that's fixed. Okay, so look at the first example. I have plate A and I have plate B. They're both moving away from a ridge, so that's my velocity of each plate with respect to the ridge. But maybe what I care about is plate B having a velocity with respect to plate A. So what's going to happen? Plate B is moving that way with 4 centimeters a year compared to plate A, or I can say plate A is moving 4 that way compared to plate B. So this is just the convention. If I have subduction zones, okay, in the second example, what do I have? I have a subduction zone. Which plate is going over and which one's on top?
The gray one is going below.
The gray one's going below. So here's a question. In the case of the ridge is always there, right? And the plates move away from it. When I have a subduction zone and this plate goes under it, how can I talk about the plate velocity B with respect to the subduction zone line? And then how would it be moving?
Sí, sí, eso está moviendo hacia abajo. Bueno, eso está profundizando.
Okay. And in the horizontal plane, which direction is it going with respect to the subduction zone line? Okay, trick question. Where is plate A moving with respect to the subduction zone line?
A la derecha, ¿no? Sí.
A la derecha? So here's the subduction zone line and plate A is moving across it.
Ah, no, no se está moviendo, de hecho. Está quieto.
Okay, so that's the key point. Did everybody understand this? Plate A has the subduction zone attached to it. Where the plate A goes, the subduction line goes. Okay, plate B goes under and it's moving, and I can fix this thing with the subduction zone and make plate B move. But if I move plate A, I'm also moving the subduction zone. Maybe this is obvious, but when you start doing velocity diagrams, that's a mistake many people make, is they forget that the subduction zone is stuck to plate A. Where plate A goes, the subduction line goes. Okay, so that's important because it's different from the ridge. The ridge, both plates move away from it. Okay, and in the case of a transform fault, the fault stays here and they move in a perpendicular direction to it. So it stays in the same place. There's no relative motion horizontally perpendicular to the fault, but it's all motion this way. So in that sense, the transform fault we consider to be fixed in this velocity space, and this plate goes up and this plate goes down. Okay. I say this because we have to remember always the reference frame issue. If I do one calculation where I fix B and then I try to calculate another part of it, but I fixed A this time, I'm going to get confused. Okay, and you'll see what I mean. So let's do a little example. Okay. Here's an example of a plate B that's stuck inside a plate A. Okay. If I have a ridge here, certain things have to happen. In this case, what has to happen? If I'm pushing B here, it's got plate A all around it, so I'm going to have to make some kind of a subduction zone on the right-hand side. Okay. Now, I don't know what's going to happen if plate A will go over plate B or plate B will go over plate A. That I can't tell just by looking at the diagram, but I know there has to be a subduction zone. And I also know that these have to be transform faults because this plate is moving this way with respect to A, which creates a transform fault. So just by knowing one type of plate boundary, sometimes you can figure out the other one. Okay. ¿Eso hasta ahora está claro? No hemos hecho en matemáticas simplemente como un diagrama conceptual diciendo, si tengo ese tipo de borde de placa, en esa configuración, yo puedo deducir todos los otros tipos de borde. Okay. Ahora, ¿qué tal las velocidades relativas? Entonces, vamos a hacer ese ejemplo. Hazlo ahora, saca un papel e intenta hacerlo. Yo tengo un ridge aquí entre placa A y placa B. Están alargando en este punto, ¿cierto? Sé que allá se tiene que subducir. Yo voy a poner el ejemplo donde la placa C es otra placa donde está encima y que la placa B va a bajar, ¿sí? Utilizando todas las velocidades relativas, puedo calcular cómo se mueve placa C con respecto a placa B.
Deberíamos poder, pero sí.
Ok, inténtalo. ¿Cómo lo van a hacer?
Jill, can you zoom in a little bit, please?
Can I see in what? Sorry?
Can you zoom in?
Zoom. Ah, see, yes. Okay, let me try to put it in presentation mode. Ah, okay. It's not letting me. Just a second. Here. Okay.
Mucho mejor.
Now you can hear. Okay.
How do you read the question?
Okay.
Velocity of C respect B, or what?
Yes. So velocity of C with respect to B. So we're going to put B fixed and say, what is C doing? First of all, which direction is C going with respect to B?
To the right.
To the right?
C.
So C is moving away from B like this? Oh no, B3. So you're looking at B with respect to C. So yes, it's moving to the right. So this is that way. You confused me. Okay, so that's right. So B is moving this way if I keep C fixed. Now, how fast? How can I start this problem? Because all of these little numbers are different plates with respect to other plates. So I somehow have to put it all in the same reference frame, right?
Sí, yo también me perdí.
Okay.
Lo de Santiago. Exactamente lo mismo. Do we fix B or C?
When let me see, well, I lost my presentation. Just a second. Where is it? Okay. When I have the one at the right, so B is at the right side of the V, that's the one that's moving, and the one on the left is fixed. So I say plate B with respect to plate C.
Plate C, okay. So we fix C.
Fix C, yes, and move B. Yes, I think I said it backwards.
Does B move to the right? Did I get it correct?
Yes, you did. So this is the arrow. We say B is moving this way, so like. See, so plate B is doing this. The question is how fast.
Okay.
So plate A is also doing the same thing. We know that velocity. So try it and then tell me how you did it. Because there's probably an easy way and some harder ways. I'll give you guys a minute to try it. See, it's easy to get confused in 1 second just by like which is fixed, but just try it.
I think it's 10.
10? Okay. Does anybody else agree? Has anybody else done the calculation?
Buenos días, ¿cómo te va?
Ay, sí le pegué, sí era 10.
Ok, entonces explica cómo lo hiciste. ¿Qué fue? ¿Lo hiciste con diagrama o qué hiciste?
No, honestamente fue suerte.
Ok,
no, mentira.
Okay.
Eso es una unidad de velocidad, por lo tanto con esas velocidades sí o sí las tenemos que sumar, porque cualquier otra operación va a dar unidades diferentes. Por lo tanto, simplemente hice como una propiedad transitiva fea, busco la B, es decir, la C a la izquierda y la B a la derecha. Por lo tanto, busco aquellas velocidades que tengan la B a la derecha y la C a la izquierda, y la sumé y ya. ¿Sí me hice entender? No, ¿cierto?
Sí, no, sí, entiendo. ¿Quién más lo ha hecho? ¿Tiene la misma respuesta? Okay.
I say it was 8.
8, okay. We have two answers, 10 or 8. And how did you arrive at that? What did you do?
I simply looked at plate A relative to plate C is moving at 6.
Okay.
Plate B is on plate A, we could say, but it also, because of the ridge, is moving at a velocity of 2 respect to plate A. But in the same direction, they are both moving. So 6 plus 2 is 8, respect to C.
Okay. How many people think it's 10 and how many people think it's 8? Those are both good arguments. So the question is, which one's right? Okay. This is where one thing that's going to help you guys a lot is what's called a velocity space diagram. And I'm not sure if you've ever done this before, but let's try this right now to think about and it will clear up this kind of ambiguity of like, wait, plate B, where's it going with respect to A, and how do I put that in? Okay, so here's the idea. I have to make a diagram that shows me velocities in space. And this is going to help because what I can do is fix one plate and recalculate all the velocities. So that's the idea. So what plate did I want to fix? I think I wanted to fix C, right?
C.
Okay, so let's fix plate C at a velocity of 0, 0, We can do this in 2D. Really, all of the motion is in 1D, so it's in X direction. Now, if I'm in plate C, where is plate A going with respect to me, and how fast?
Esa la dice. Va
That's
6.
it. 6.
6 a la derecha.
Okay, so if this is a velocity diagram, this is velocity in Y direction, and this is velocity in X direction. So instead of plotting positions, I'm going to... So the X direction is velocity in X. So if I can put A here. Okay. Oh, I'm not drawing the A very well. So what does this mean? This means that if this is 6, it doesn't matter the unit, 6 centimeters per year, let's say. I am placing A to the right of C on my velocity diagram, which tells me that A is going this way with respect to C at a velocity of 6. So these are velocities, okay? Now I can look at where A is and say, okay, I have this plate B that's also moving. But if I compare it to plate A, I don't know how it's going with respect to C, but if I compare it to plate A, that I can do the comparison of. And where is it going with respect to plate A?
2 units to the right.
2 units to the right?
No, de hecho son 4. 4 a la derecha.
Okay, so this is where the trick question came in. Remember, I mentioned with the problem with ridges is that we tend to do this thing because we say, oh, it's like it's a parallel situation. I have a mirror image, and so it goes 2 and 2. But this 2 is really with respect to the ridge. If I look at how fast plate A is moving away from plate B, it's 4. Okay. Because if I fix plate A, all of plate B is moving away at 4. If I fix the ridge, they're both moving at 2. And if I fix plate B, A is moving away at 4. So that was the trick part here. I have to put plate B 4 units to the right of plate A on my velocity diagram. So 1, 2, 3, 4, and this is 10. Okay. So be careful with when these diagrams, they always put 2 and 2 or something like this. That's the velocity with respect to the ridge. I can put my ridge on this diagram too. Let's put the ridge. Where's the ridge? The ridge is moving to the right of plate A, and it's moving to the left with respect to plate B, right? It's halfway in the middle. So if this is A and this is B, my ridge would go here. Okay. So I can now say, actually, the ridge is moving to the right with respect to plate C at 8. And I can put everything in terms of plate C. So what will eventually happen to that ridge? Will it keep going?
No, también va a subducir.
Yeah, that ridge is moving towards the subduction zone at 8. And so eventually it will subduct completely. Okay, so that's your first little plate reconstruction. Does this remind you of anything that you know? A plate that you know? South America, North America. There's my bad drawings of the continent.
Jill, someone
Yep.
is asking if you could repeat the exercise in Spanish.
Ok, listo. Ok, entonces lo que estamos hablando es tener lo que se llama un diagrama de velocidades. Entonces, especialmente en lugar de plotear ubicaciones, voy a plotear velocidades. En este caso, lo que tengo es un X y Y, que son velocidades. Uy, se me pasó. Se me volvió. Y entonces, en velocidad de X, si quiero fijar una placa, lo pongo en 0, ¿sí? Entonces, la placa C decidimos que está fija, lo pongo con velocidad de 0. Todo lo demás yo voy a poner en el espacio de velocidades comparado con eso. Entonces, la primera parte de la información que tengo ya es cómo se mueve placa A con respecto a C. En este caso va 6 unidades a la derecha, entonces lo pongo aquí, donde eso es 6. Ponemos centímetros, las unidades no lo tienen. Bueno, entonces yo tengo A moviendo con 6 a la derecha con respecto a C, que está en 0. ¿Okay? Para ser consistente, necesito hacer todo en ese mismo diagrama con C en el origen, a pesar de que la información del diagrama son diferentes marcos de referencia. Por ejemplo, esa cosa de 2 realmente representa que el B va a la derecha con 2 y A a la izquierda con 2 con respecto al ridge. Pero el ridge no me interesa la placa C. Entonces, ¿qué hago? Necesito poner en mi diagrama, no sé si puedo, bueno, yo voy a dibujar aquí para que sea más clara. Si tengo C en el origen, eso es BJ, que a veces uno necesita 2 dimensiones, ahora no. Okay. Yo sé que A está moviendo a la derecha con 6 unidades con respecto al origen, que es C. Y ahora, ¿qué más sé? Yo sé cosas sobre A, porque mira que placa A también está moviendo con respecto a placa B. El ridge lo dibujaron así porque es la convención en muchos mapas que poner el ridge aquí y las velocidades con respecto al ridge al lado, 2 y 2. Pero si fijo placa A en este momento, ¿dónde va B? A 4 con respecto a A. ¿Sí? Es el doble. Entonces yo tengo que poner el B a la derecha porque va hacia la derecha con respecto a A, entonces va más a la derecha que A, con 4 unidades más. Entonces esos son 4, esos son 6. Entonces la velocidad de B con respecto a C es 10. Okay. Pero ya como acabo de mencionar, todos los bordes también se pueden colocar, ¿cierto? El ridge va ¿dónde? Pues aquí lo tienen fijo y placa A haciendo eso y placa B haciendo eso, pero en realidad si lo comparo con alguna de esas placas, va en la mitad, porque así B va 2 a la derecha y A va 2 a la izquierda, entonces si comparo con C, el ridge va a 8 con respecto a C. Y yo puedo también poner la zona de subducción. ¿Dónde va la zona de subducción?
En 0, en 0.
En 0. En 0, ¿por qué? Porque está pegada a la placa C, entonces fijada. Aquí. Sí. Entonces el trench está aquí, el ridge está aquí, placa A va aquí y placa B va aquí. Y todos con respecto a C. Yo pongo C con velocidad 0 y todas las otras placas los coloco en el diagrama. Y ahora sí tengo un concepto muy fácil. Yo puedo decir, bueno, ese ridge está moviendo hacia la placa C así, con una velocidad de 8, así que va a subducir. Y yo puedo hasta calcular el momento en que va a subducir. Okay. ¿Ya todos quedaron claros con eso? ¿O hay dudas? Son como esos problemas en física 1 donde alguien como arranca para cruzar un río y con respecto al río va a una velocidad así, pero que si lo miro con mi amigo que está por allá, parece que tengo una pista así, es igual. Lo que pasa es que aquí como tengo muchas cosas y la descripción son todas diferentes velocidades relativas, me toca ponerlo en un marco de referencia y calcular todo en el mismo. Y eso es más fácil si pongo diagramas de velocidad. Okay. Eso es parecido a lo que está pasando en la Nazca. Sí, esa es la placa Nazca que va debajo de Sudamérica. Tenemos un ridge aquí y una zona de subducción aquí. Ustedes como ejercicio podrían decirme si ese ridge va a subducir eventualmente, si se queda allá, si se alarga y con qué rapidez. Con ese mismo ejercicio pueden hacer esa pregunta. La primera vez que dicté ese curso puse eso como tarea, lo de Nazca, y todos estaban como, ¿qué es eso? Entonces prefiero hacerlo como un ejemplo que ustedes pueden hacer y así todo lo que pasa después se puede hacer de la misma forma. Y uno puede como decir, bueno, ese que está acercándose a Norteamérica, donde tengo un ridge, tengo una otra cosa, tengo un ridge, tengo otra cosa, ¿qué va a pasar con el tiempo? ¿Ese ridge queda o subduce? ¿Ese también o subduce? ¿Y qué pasa cuando por fin se tocan? ¿Sí? Y solamente con esos diagramas se puede hacer todo. ¿Sencillo o complicado? ¿O todo bien? ¿Por qué es 4 en lugar de 2? Ok. Cristian tiene, el ridge está moviendo a 2. Sí, si lo ponemos en términos de ridges, vamos a poner un perro. Yo tengo un perro, okay, que se queda aquí. Y bueno, eso es el peor dibujo del perro que he visto. Y yo estoy aquí con mi amigo. Ok, estamos aquí. Yo le digo, 1, 2, 3, vamos a correr en direcciones contrarias. A la misma velocidad. Primero, ¿qué es lo que ve el perro?
Que ambos se alejan.
Ok, ambos se alejan. Digamos que el perro me ve alejándome a 2 y mi amigo alejándome a 2. Pero si mi amigo puede mirar sobre su hombro y verme a mí, ¿qué va a ver?
Que me estoy alejando a 4.
Exactamente. Entonces, este diagrama lo que está diciendo es que aquí el perro está viendo ambas placas haciendo eso. Pero si me interesa en algún momento cómo mueve la placa B con respecto a A, eso sí tiene que ser 4 porque ese está alargando mientras me estoy largando. ¿Un poco confuso todavía? ¿Ya? Ok.
No, pero eso estuvo bien, esa explicación.
Ok, listo. Sí, porque obviamente es que mucha gente tiene miedo de la matemática en geodinámica, pero no es la matemática, es tener muy claro el concepto y luego la matemática es facilísima. Lo que pasa es que para poner el problema en los términos que son, esa es la parte difícil. ¿Cuál es la duda?
CBB es la velocidad de C con respecto a B o la velocidad de B con respecto a C.
B con respecto a C. Entonces, la placa que se mueve siempre es a la derecha. Eso por convención y casi todos los libros lo ponen así. ¿Sí? Pero lo pueden hacer de otra forma. Yo creo que es más, a veces lo ven así también. Y siempre es que a la derecha es la que se mueve. Sí. Yo no he visto ejemplos donde lo hacen de contrario, puede ser, pero deberían decirlo entonces. Pero todos los libros que he visto, como lo hacen en esta forma, preciso para no confundir la cosa. Ok. Bueno, entonces en este diagrama aquí mi amigo, aquí soy yo, aquí el perro en la mitad y ahí a la placa C por ahí. Okay. La dirección está bien porque lo que es raro es que la posición de las placas en espacio es muy distinta a la posición en espacio de velocidades, ¿cierto? O sea, si en este diagrama la placa C queda a la derecha de todas las otras placas, pero si lo fijo, automáticamente lo mando al origen y solo quiero ver la dirección de movimiento de cada placa y entonces lo ubico en espacio de velocidad y puede parecerse diferente. Entonces hay que tener mucho cuidado con qué quiere decir ese espacio de velocidad. Y a la derecha significa que se mueve hacia la derecha, no que esté ubicada a la derecha. Es la última cosa que puede confundir. Ok, con todo eso ustedes pueden hacer el problema número 1. Ok, con más de 2, o sea, con una intersección de varias placas, eso se puede confundir. Mire, tenemos 2 triple junctions aquí. ¿Cómo se llama un triple junction en español?
Triple intersección, tal vez.
Sí, tal vez. Aquí tenemos intersección de placas A, B y C. Y placas A, B, C también aquí, ¿cierto? Eso pasa mucho en la Tierra. El ejemplo que les di en la tarea es entre Pacífica, Antártica y Australia. Y hay muchas más. ¿Okay? Una cosa interesante es que yo puedo calcular hasta dónde mueve ese punto con respecto a C, por ejemplo. En este caso no pasa nada porque es como eso queda fijo y entonces la triple intersección también está pegada a ese punto porque si no, no es un triple junction. Entonces también tampoco se mueve. Pero hay complicaciones donde uno puede tener triple junctions que se mueven a diferentes lados o que se deshacen en un momento a otro. Y entender que la evaluación de los triple junctions también nos da algo sobre la evaluación de las posiciones de las placas. La única diferencia entre eso y esta situación que acabamos de hacer es que es en 2D y no en 1D. Entonces yo estoy poniendo velocidades en Y también, que vamos a hacer un ejemplo. Y el triple junction también es una cosa que puedo ubicar en mi velocidad, en mi espacio de velocidades. Si no queda en el origen, entonces está moviendo, básicamente. Si está moviendo en diferentes direcciones según cómo hago el triángulo, es porque es inestable. Y vamos a ver eso. ¿Listo? Ok, bueno, aquí el análisis. Okay. Si tengo la posición Y también, un movimiento hacia arriba, yo hago exactamente la misma cosa. Ahora sí quiero ver cómo mueve la placa B con respecto a la placa C. Es exactamente igual que lo que hicimos a partir de que ahora sí tenemos una complicación que es movimiento así. Pero yo les dejo hacer eso en la casa para traerme preguntas, porque la única diferencia realmente es que tienen que hacer eso. Ahora sí, Jay. Dime.
No, lo siento, no, perdón.
Okay. Entonces, intenta ese ejercicio en la casa y hablamos, si quieren, el jueves de qué hallaron, porque la idea aquí es no todo es movimiento hacia aquí, sino cosas moviendo aquí, cosas moviendo aquí, y eso es un poco más complejo, pero es igual, es que la misma cosa, el perro ahí está viendo de pronto una persona yendo por allá y una persona yendo por allá, y cuál es la velocidad entre las personas, pues ahora sí va a ser triangulitos, pero es igual que el otro problema. Entonces yo les voy a dejar hacerlo, si el triangulito. Hay más ejemplos, ¿ok? Y uno puede hacer miles de ejemplos. De hecho, les recomiendo una cosa. En el libro Fowler y en el de Tucker y Schubert tienen muchos ejemplos de esas configuraciones de bordes de placas, de junctions y eso, para hacer ejercicios. Y uno puede, por ejemplo, ver, no sé, hay una cosa que uno puede hacer donde, digamos, yo tengo uno que va así, y no sé, eso es un borde de subducción, eso es una cosa transformante, el otro es un ridge, y uno puede decir, bueno, esta placa, ¿dónde va con respecto a esta? Ok, y esto, ¿dónde va con respecto a esto? Y si tengo un par de velocidades y un ángulo, o tengo un par de ángulos y una velocidad, yo puedo hallar todo lo demás. Ok. Entonces, intentan los ejemplos que están en los libros, porque una cosa es entender el ejemplo sencillo y otra cosa es aplicarlo a situaciones un poco más complejas donde es fácil confundirse. ¿Listo? Entonces, yo les puse estos ejemplos para practicar. Y yo, en mi experiencia, lo que pasa es que yo puedo explicarlo 1000 veces, pero no hay sustituto que para ustedes haciendo el ejercicio y traerme dudas, porque yo puedo explicar cómo sea y luego uno tiene el problema enfrente, uy, ¿cómo era? ¿Cierto? Entonces inténtalo, intenta ese ejemplo que está en la presentación y si tienen dudas, hablamos de las dudas el jueves y despejamos todas las dudas de una vez. Okay. Is it possible to have plates moving differently towards each other with respect to each other? Yes. Ok, Santiago, eso es una pregunta muy interesante porque de hecho pasa. Yo, como tengo la tierra, o sea, las placas rotando realmente, yo puedo tener un borde de placa que hace así, donde aquí hay subducción y aquí ridge. O miramos el ejemplo donde hay ridge aquí, pero es más rápido aquí que ahí. Y generalmente a gran escala siempre es así. Yo tengo bordes de placa de... Bueno, ¿cómo es el borde entre Pacífica y Norteamérica? Depende de dónde. Todo eso tiene una lógica del movimiento circular que uno puede calcular simplemente mirando los polos de Euler. Es decir, yo tengo aquí una rotación. ¿Cuál es el eje de rotación? Probablemente esto, ¿sí? Entonces, si todo rota hasta aquí, hay un lado donde de pronto tengo subducción al lado contrario y apertura aquí. De hecho, si el planeta tuviera solamente 2 placas y intento abrir aquí, ¿qué pasa? Aquí se cierre. Entonces, por eso digo, si uno pregunta la velocidad relativa entre placa A y placa B, la primera pregunta que tengo es ¿dónde? ¿Sí? Porque si este lado es una zona de subducción y este lado es un ridge, pues las velocidades son súper diferentes. Entonces, tienes razón, Santiago, y muchas gracias. Eso es un punto muy importante. Por eso, cuando estamos hablando de esas cosas en plano, es porque estamos mirando un área chiquita y estamos asumiendo que en esta parte del ridge la velocidad es igual aquí. Entonces, si quieren hacer el ejercicio de Nazca, van a ver que la velocidad del ridge varía por todo lo largo del ridge. Yo puedo hacer ese problema sin molestar por velocidades porque lo puedo hacer todo con velocidades angulares y ahí me ahorro el problema. Pero si lo hago con velocidades lineales, hay una variación entre el norte y sur que es notable. Entonces, sí. ¿Todo claro? Listo. Okay, so I'm going to go back to English now. Stop me again if it's not clear. Why are there so many triple junctions? And why don't we see 5 plates touching or 10 plates touching? Why do you think that happens? This is a weird question, but if I take a piece of paper right now and try to draw, which I can't find my pencil. Where's my pencil? I've lost my pencil. But try it yourselves. If I have a little notebook here, draw a bunch of lines and just make them intersect randomly. Or you could do it even more fun if you have like a big cookie and you try to break it into pieces. Does it look like this pie? I can make a pie slice and I can make 100 intersecting plates if I want, pie slices. But if I crack a cookie, it doesn't seem to work that way so much, right? Or if I draw lines randomly on a paper. What kind of junctions do I get? If I just do a cross like this, my first line cross, tunk, I get 4, A, B, C, D. So I can get quadruple junctions easily. If I want to make 5, I kind of have to do it on purpose, right? And I have to draw a line to make it meet in a point like the pie. If it's random, it's not so likely, but there seems to be, if I draw a bunch of lines on a thing, try it. What's the maximum number that you get intersecting? Nobody has paper nowadays, right? Maybe you do have to. Do you guys take notes by hand? Okay, Christian, so you say 4. That's what I would get randomly myself. I've done this exercise before, so it's normal to have 4. So why on the earth, if I crack up all the plates, do I not see a whole bunch of quadruple junctions? We have to look at a picture of a... Let's look at this. So this seems that there's a little bit of a difference between drawing lines on a page and breaking up these plates. I have a lot of borders between 2 plates. I sometimes have an intersection between 3, right? Oops, if I click on it without the pen, it goes away. Okay. So this is an intersection between 3. I have another one here. I have another one. So many. Look at all the triple junctions I can find here. There's probably dozens and dozens of triple junctions in the world. This is the one I asked you to do for homework, I think. Nope, that's a different one. This is the one I asked you to do for homework. But there's also one here. So I can ask you any number of one of these and you should be able to do it with the velocity diagram. But there's literally dozens of triple junctions. But quadruple junctions, really in this map, I see one. Maybe when there's microplates, I can find another one or two. Why do we not see those? What are these plates doing? What do you think? Juan Pablo?
Maybe because they are unstable.
Okay, why are they unstable? What does that mean?
I don't know. But I guess that maybe that configuration of plates it's unstable and tends to become a typical tree configuration.
Okay. So that's the basic idea. The plates are always moving. Let's look at this quadruple junction we have here. This is the subduction zone, right? So what's going to happen in about 1 million years? Boom. This thing gets subducted, and now I have a triple junction, another triple junction. This is gone. This is all underneath the plate now. And suddenly, I now have no more quadruple junction. This is what usually happens. If I have 4 plates meeting in a moment, the fact that the plates begin to move will usually destroy that little point and make it into something else. Maybe 2 triple junctions will come out of it. Okay, so it's there now. It'll probably be there for the next 1 million years or so, but it'll begin to subduct and eventually disappear. So it's not just a matter of drawing lines on a thing, but breaking something up into pieces. And when I take, you guys can try this with a cookie if you want. If you don't cut it like a pie, but just start snapping bits and then hold it together, you will find some quadruple junctions. But if I try to move the pieces around, I'm going to start covering up those quadruple junctions or separating them, and it disappears very quickly. So on a sphere, we can really move plates around and have them meet at 3 at a time, but it's very unusual to have more than 3 at a time. I'd really have to have a thing where I fracture up Eurasia, for example, and have many, many plates like this. And then what would happen? They'd begin to move, and it would erase again all these places where it meets at a point, because the casualty of mating 5 plates at a point, all I have to do is move 1 plate and I erase a couple of them. Okay, so it's not, it doesn't last long. That's just an interesting thing. So mostly what we'll do is analyze plate borders and maybe the meeting of 3 plates and nothing else. The ones with 4 don't really work. So here's a very simple example, right? I draw my line on a page like this, boom. Now I can have different types of plate boundaries, but what will happen is, let's say I have a ridge. Now, if this ridge is exactly the same as this ridge and they're moving at the same space, there's no border here. It's the same plate going like this. So in order to make this extra boundary, I have to move maybe this ridge faster than this ridge. Okay, that can happen. But if you look at what happens in time, what will happen to this? If this is perfectly right angles and on a flat surface, it may survive. But what is really happening on the Earth is these plates are rotating like this. This one's subducting here, so this will subduct quickly, and I'm going to very quickly get rid of that. If it's perfect situation like this, I could make this go on for a little while, but eventually one or both of them will subduct. Because this is really a rotation, at some point this will go like this, and this will stop being a ridge. Okay. At some point, if the velocities are equal, then this boundary no longer moves, and I no longer have a fault, and so I just have a simple boundary. Okay, so it's very short-lived, and you can try to convince yourself by ripping up pieces of paper and trying to move them around and seeing if you can keep a quadruple junction around for a while, but it's hard to do. Okay, anyway. So quadruple junctions are not stable. What about triple junctions? This is kind of fun. Triple junctions can last a long time. In fact, they can last forever. Some plates, for example, where I have a spreading center between these two, and these two, will just keep spreading forever, and I'll have a point where they all meet, and it'll stay there forever. Forever means till the next Wilson cycle before a big continent runs it over. But it will be stable for many, many millions of years. Some are not. say, also disappear. Okay, so this is a big, don't worry about, oh God, I have to know what's all on this slide. No, these are examples. Basically, there are 16 possible combinations of triple junctions. We have 3 types of plates, which are 3 types of boundaries which meet 3 at a time. So we can have, for example, all ridges, all faults, or all subduction zones. Or I can have one of each kind, or 2 ridges and a fault, or 2 ridges and a subduction zone. So it's actually 16 possibilities. If we want to know how long they'll last, we have to do a stability analysis. Some of them are always unstable, some of them are always stable, and some of them depend on the velocities. Now, this is a fun exercise. You use the same kinds of diagrams that we just did. It's all velocity diagram. So this is what I meant about the looking at the bathymetry map. If I want to find my triple junction that's in the homework, I have what? Australia and Antarctica and Pacific. So that would be Pacific, or is it Indian? No, it's over here. Oh, I can't see it very well. We have Pacific plate and Antarctic and Australia, so like here.
Excuse me, are you drawing?
Can you not see the drawing? There's a pen.
Ya lo siento.
Okay.
Sí.
Okay, so scary. If you can't see what I'm drawing, then this makes no sense. Okay, so you can go actually just looking at bathymetry and find the triple junctions, right? You can see them. It's kind of cool. Now, what do you think the stable ones might be? Do you think this one, for example, where Nazca and North America and Caucasus are meeting here, or Nazca, North America, and Antarctica are meeting here? Wait, I don't know if it's this one or this one. Are these stable? And what do we mean by that? Stable means they're going to continue to exist. Unstable means maybe in a million years they'll be gone and turned into something else. So if I just look at the area around, is this triple junction going to still be a triple junction a million years from now, or does it think it will disappear? How do I know? I actually have to do a future prediction with my plates. Okay. And how am I going to do that? Just with my plate velocities. So I have to say, okay, I have the velocity of these 3 plates now. If I project into the future, am I still going to have a triple junction? Will one of the plates disappear? Will I end up with just a simple plate boundary? Will I end up with 2 different triple junctions? What will I get? So that is one step further. What I had to do was find velocities in velocity space, and now say, if I use those velocities to move all the plates to where they're going, what will I get? Okay, so that's the second piece of doing a plate prediction, I would say. You can also do it as a plate reconstruction by going backwards in time. Okay, so it's the same idea. Where were those plates before, or where are they going now? And I just use the velocities to move them in time. So here's my favorite example. 30 million years ago, so this was a backwards for plate construction, but which we can start in the past now and move it forward with our velocities. We have the North American plate, the Pacific plate, and there's this other funny little plate, Farallon plate, okay, that touches the Pacific coast of North America. Back in time, we probably had something like this, a ridge offset by subduction, by transform faults, right, as you get with a plate that's opening. And it comes to North America where there's a subduction zone. What happens? Here, the minute my ridge touches, I'm coming in at an oblique angle, which is maybe also, Santiago, what you meant. Instead of having an encounter like this, I could have an oblique encounter, right, in the subduction zone. I maybe don't subduct perpendicular, I subduct angled. A funny thing happens. I end up, as soon as this touches, in order to be self-consistent with all the velocities of the plates, I have to have a transform fault here forming. So what did I do? I created a new triple junction that didn't exist and another new triple junction that didn't exist just by subducting a ridge. Okay. So today, what I have is San Andreas fault subduction zone. What will happen in the future? Probably this will subduct completely. Now, what are my options? The Pacific plate could keep coming and still have a subduction zone, but now instead of Farallon South North America, I could have Pacific North America. Or I could turn it all into a transform fault. Okay. This comes from a paper by Stouffer on Where's the San Andreas Fault, where they walk you through a little bit of how you reconstruct this history and what do you think will happen in the future. Now, this is a complicated example, but it is actually predictable based on the current plate velocities. Okay, so we can do some simpler examples. Let's look at this triple junction. This is a real one. This is San Andreas Fault. This is the Farallon plate. We simplified a little bit, North America Pacific. The question is, this point that's on my plate in top of the subduction zone, in the future, is it going to become still a subduction zone? Will it turn into a transform fault, or will it be something else? Okay, it all depends on what happens here. I've created this triple junction by subducting a ridge. Now that I have it, where's it going? Is it going to move south? Is it going to move up? Or is it going to disappear? What do you guys think? If the triple junction moves up, I know that eventually my E is going to be next to a transform fault. If this moves that way, all of this is going to turn into subduction zone. So E will stay a subduction zone. But how do I know where this is going with respect to that point? So what we have to do is a little velocity space example again. Okay, we have time to do this one. Triple junction stability, first of all, means that I can point and plot my triple junction velocity space. If it has a spot in my velocity space and not, for example, more than one spot or no spot, it means it's stable, right? It has a velocity, it's moving with respect to these plates, and it's still a triple junction. So how do I know if that's true? I have to actually find the velocity of the plates with respect to whichever one I want to fix, the velocity of the borders, and what is the definition of a triple junction? The intersection between three plates. So this triple junction has to be consistent with the velocity of this border, and this border. If it has no consistent definition, it means that's going to separate and turn into something else. Okay. An example of what would happen, let's try an example right now without the numbers of a trench, triple junction. All of these are subduction zones. What happens to this point? This one is subducting under here and under here. This one's subducting under here. Okay. This one is going over this. So what's going to happen? This is going to move along here, but because this is subducting, it'll get consumed. So this plate maybe will run over this, and you think, oh, the triple junction will just move, but look how this plate is also going under this one. So what'll happen is this will move and get subducted under, and it disappears. So the question is, how can we put that quantitatively? How can we say what will happen? And that's when we have to do this thing. So maybe you guys want to try it. I don't know if we have a lot of time to try this. This is the last sort of topic for today. We have a few minutes. Fix C and make your velocity diagram. I'm going to do it right now. Here's my velocity diagram. I fix C. Where is B going?
Hacia arriba.
Okay, so
Dos
B
pasitos.
goes here.
Dos
Exactly.
pasitos hacia arriba.
Dos pasitos hacia arriba. Perfect. And A, with respect to C, where is it going?
Four steps forward. Up. Four steps up. Sorry.
With respect to B.
Sí.
Okay. So what's it doing with respect to C? It's also moving up, but 6, right? So 1, 2, 3, 4, 5, 6. Okay. So that's good because this means it's 4 going up
Plus
4
2.
with respect to, and just 2 with respect to, so it's all in a line. That's good. Where's the triple junction? What we have to do is find the boundaries, okay? So, where does the subduction zone go? Remember?
Esa sube, tiene que subir.
¿Con qué velocidad? Con respecto a C.
4, tiene que... No, eso es 4. Ay, mentira. Wait. 2, de hecho es 2. Mentira, no sé. Pero creo que es 2.
O sea, aquí.
Sí.
Ok. Recuerden lo que pasa cuando tengo un borde de subducción. Eso viene siempre acompañado con la placa que va en arriba. ¿Sí? Si eso es mi placa arriba y yo tengo cualquier cosa pasando de subducción y eso, el borde va con la placa que va arriba. Entonces, ¿qué significa? Si yo tengo un borde de subducción A con B y la placa encima es A, ese borde tiene que estar pegado a A. Aquí. ¿Sí? Entonces, es el borde de subducción de trench. Con respecto a C, está moviendo así. ¿Cierto? Y estos bordes, ¿qué vamos a hacer con ellos? Como B y C están haciendo esto, el borde tiene que estar pegado a ambos. Entonces van así. Ambos. Donde hay intersección, triple junction. ¿Qué significa eso? Eso es el borde de las placas en espacio de velocidad. Si el triple junction tiene diferentes velocidades con respecto a los bordes, ¿qué va a pasar? Va a desaparecer. El triple junction permanece si siempre está moviendo de forma que esté siempre pegado con los 3 bordes, porque donde se despegue ya no es una intersección de 3 bordes. Pero además, mira, que está moviendo, ya lo ploteé, y con respecto a C, entonces está moviendo a 6 hacia arriba, está moviendo así. El triple junction. ¿Por qué? Porque lo único que pasa en ese diagrama es que eso va moviendo así, más arriba, más arriba, más arriba, y con él se mueve el triple junction. ¿Sí? Pregunta número 2. La respuesta es 1, es que sí se mueve el triple junction. ¿Qué pasa con el pececito? ¿El pez va a subducir o no?
No.
¿No? ¿Dónde va el pez?
Ah, no sé. ¿Se queda quieto o no?
Con respecto a C, ¿qué hace el pez? Esa es la pregunta.
Con respecto a ese, se mueve hacia arriba.
Sí, sí, sube, sí.
Ok. Entonces el pez mueve así. Solo sin nada muy rápido.
Pero se va a subducir.
Se va a subducir. ¿Por qué? Porque mire, como eso va marchando hacia arriba, si el pez no se mueve, es consumido por placa A. ¿Okay? Entonces yo lo que quiero es que ustedes, ya estamos acabando el tiempo o no, ya tenemos, sí. Hagan los ejercicios que están en esta presentación y miren la parte interconjugate. ¿Ustedes tienen el libro? ¿Han conseguido el libro?
Sí, sí, yo lo conseguí. Ambos, de hecho.
Sí, eso está buenísima porque sobre todo en Fowler hay muchos ejemplos. Intenta esos ejemplos hasta que se convenzan que pueden hacer ese diagrama para cualquier problema. Yo sé que es mucha información. El jueves, si quieres, tráeme sus dudas. Empezamos con eso porque luego tenemos que empezar a hacer como introducir la parte de esferas. O sea, que no solamente en el plano, sino esféricamente, donde hay rotaciones y eso. Entonces se complica. Lo más prudente es tener eso muy, muy, muy claro antes de seguir. Y intenten los ejemplos, honestamente. Yo sé que están muy ocupados, pero haz 1 o 2. Y si no logran, pregúntenme. ¿Listo? Pero siempre el mismo principio. Pone con cuidado el diagrama de velocidades y ubica todo con la información que hay hasta tener una imagen consistente entre todos los posibles movimientos de placas y ubicar el triple junction. Bueno, nos vemos el jueves. Yo voy a intentar ponerles más ejemplos, pero casi todos que están en Fowler y Schubert, todas las posibles configuraciones y todas las posibilidades. De hecho, haz el problema 1 de la tarea de una vez y así me pregunta. ¿Listo? Que esto es un ejemplo de triple junction. Ok.
¿Dónde está la tarea? Yo no la encuentro.
¿No lo encuentran? Déjame ver.
En actividades.
Actividades.
A mí
Sí,
me parece vacío eso.
Actividades.
No, entonces no lo tienes que hacer.
¿Qué tengo que hacer? Yo creo que me toca siempre volver a hacerlo visible 2 veces o algo así que me dijeron. Actividades. Tarea 1. Pues yo veo en mi cosa que parece visible, pero editar. No sé. ¿Hay alguien que la ha visto?
Yo ya la vi y de hecho creo que Sergio también porque hizo una pregunta en la tarea.
Ah, ok. Entonces, toca buscar porque debería ya estar. Yo lo puse como vigente desde ayer.
Ok, ya volví a recargar y ya me volvió a salir.
Ok,
Hace
listo.
literal como 15 minutos me parecía vacío.
Ok, listo. Ok. Bueno, entonces cualquier problema de este tipo o de otro problema me avisan y hablamos el jueves. ¿Listo? Ok. Déjate grabar aquí. Ok.